So quiz number 3 for 2021. A couple things for part number 1. Make sure we added all lone pairs to all below. I want you to draw the mechanism and resonance arrows to form the intermediates and products. Fill in the molecule for intermediate B. Then circle the thermodynamic product. So first step, really you should number your carbons. Right? In this case, I numbered the diene, di as in 2 alkenes, and these are of course conjugated. They can do res with each other, but I numbered them. It doesn't matter how you numbered them. I just did it this way. 1, 2, 3, 4. And make sure I'm consistent with that numbering throughout. I'm having this alkene be the nucleophile, react with HCl. I chose this alkene because it gives me the most stable intermediate. It gives me a tertiary carbocation, a tertiary allylic carbocation. Pi bond reacts, puts the hydrogen on carbon 1. So this hydrogen ends up on 1. Make a Cl minus. The Cl minus acts as a nucleophile, reacts with carbon 2. And that's what leads us to product A. We call this the 1,2 product because something added, hydrogen added to 1, the chlorine added to 2. Alternatively, from intermediate A, you could do a resonance structure where the pi bond between 3 and 4 moves, those 2 electrons move to make a new pi bond between 2 and 3, and the carbocation results on carbon 4. From there, the chlorine could react and react with carbon 4. Now, intermediate B is actually less stable than intermediate A because this is a secondary allylic, while this was tertiary allylic, so it takes some energy to get here. But if it does, if we make that intermediate, the chlorine can react with carbon 4. And this is an SN1 type thing. And we end up with a 1,4 product. The hydrogen added to carbon 1. And the nucleophile, the chlorine, ends up adding on 4. Now, so we've drawn intermediate B, we've drawn the arrows. The other big thing is which one of these is the thermodynamic product? Well, thermodynamics asks us about the product stability. So which one of these products is the most stable? It's actually product B. Why is product B the most stable? It is the most stable because it has the most substituted alkene. That's Zaitsev's rule. Zaitsev's rule. So if you want to look that up, Zaitsev, right? So this is the most stable product, but it came from a less stable intermediate, right? So this product A is actually the kinetic product because it comes from the more stable intermediate. Thermodynamics only looks at the stability of the products. Kinetics looks at the activation energies. This would be easier to make, have a lower activation energy because it's a more stable intermediate, so it leads to this product, even though this product is not the most stable. Intermediate B is a less stable intermediate, but it leads to a more stable product. I would advise, if you want to see more of this as in a free energy diagram, to take a look at one of our the 1,4,1,2 additions reaction video. That's informative and it'll show you this also in a free energy diagram sense to review that. It was one of our pre-class survey questions. All right, number 2 says draw the mechanism arrows on the starting materials. So these are the starting materials on the left to form the products. So the mechanism arrows, nucleophile, electron density, that's where the arrows start. Reacts with the hydrogen to break the CH bond. How do I know that's the bond to break? Because I looked at the products. I see there's a negative charge here, and this H must be that one. So the 2 arrows. Will the starting materials or products be favored in this equilibrium reaction? Briefly explain your answer. So in this case, the starting materials will be stable, but will be favored. And how do I know that? Well, I look at the differences. Negative charge. Obviously, so charge is balanced. This is a negative charge in an sp hybrid orbital. This is a negative charge in an sp3 hybrid orbital. So what's the difference? Well, an sp hybrid orbital is shorter and fatter, more s character, 50% s, 50% p. An sp3 hybrid orbital is 25% s, 75% p. So the lone pair here is farther away from the nucleus. If you're close to the nucleus, the charge in the nucleus is positive because it has protons. So you want to be closer. That's going to make it more stable. So this sp hybridized with a negative charge in a lone pair is more stable than an sp3 because this is the shape of the sp orbital puts the lone pair is closer to the nucleus, which is positively charged. All right, for this one, label the molecules below as acid or base. Draw the mechanism arrows for the forward acid-base reaction. Now forward just means from left to right, forward. And will the starting materials or products be favored in this equilibrium reaction? And briefly explain it. So 2 arrows. The plus charge should tell you that's an acid, that's an electrophile. The lone pair from this oxygen reacts with the hydrogen, breaks the OH bond, even though there's a plus charge in the oxygen. The electron deficiency is at the hydrogen. So this is an acid, this is a base. acid again, plus charge, base. So the arrows and the labeling there. What will be favored? The star materials will actually be favored because this lone pair is less reactive because it can do resonance, right? So it makes it a less reactive base. So because of that, it's less likely to react and is more stable with this. So this is a less reactive base than one that can't, that's not able to do resonance. So something that's not able to do resonance is going to be more reactive. So because this is less reactive, this will be the more stable side. Less reactive, more stable. Number 4, draw the most stable resonance structure, including arrows for the molecule, and explain why it's the most stable resonance structure. So showing the molecule below, we have a carbocation, that's an allylic carbocation. When I had done here, I have the electrons come down from the lone pair, pi bond electrons move, and that gives us this, right? We've balanced our charge, so there's a plus charge on the oxygen, but if you notice, everybody has a full octet. So the reason why this is the most stable is because it follows the octet rule. So more stable octets, more stable molecule. If you have a full octet, more stable molecule. So even though there's a plus charge in this oxygen, because there's a full octet, this is a better resonance form. All about the octet rule. So this is really lone pair combined with pi bond resonance to get there. And you could have done this in 2 steps if you wanted to. I just did it in 1 to get it there.